Greetings, hello, hey there, welcome. So let's get this problem down. I, what I mean by that, let's conclude what we started. There's been a nice journey, and now it's about to come to an end, okay? So in this video, we'll just be finishing off with the problem that we have been solving so far. So let's go ahead and find the efficiency, find what is our heat lost from the condenser, and what is the heat that is added to vaporize feed water into steam. Okay, so that's the purpose of this video, to find the mass flow rate, the efficiency, and then it's done. It's done. The problem is done. All right. Let's get started. So, what are we given? What do we know from the problem? We're given that the net power output of the plant is 400 megawatt. So work net, and the formula for work net is as follows. Work of the turbine, work of the turbine minus work, input work to the pumps, minus work pumps. When I say minus work pump, I mean total work of the pump, because we have two pumps in here. You'll have work and work. All this work is consumed by the two pumps. What I mean by that, pumps are work consuming devices, so they consume work, while as a turbine is a work producing device, so it produces work. Hence, we like turbines because they give us work. We don't like pumps, because they consume work. But yeah, they are all needed in a system. That's why we subtract pump work from turbine work to get useful work, which is our network. Okay. And the formula for another formula is, if you don't want to use turbine work and pump work, we can go through, you can use heats, can use heat, which is Q dot heat, fed to the feed water, and heat that is being lost from the condenser, QL. Q dot minus QL. Yeah, so I can use either of these to get M dot that we're looking for. Yes, but the problem gives us that work net is equal to 400 megawatts. So megawatts times 10 to the power, what is this? 6 watts. Let's convert this to kilowatt. Times 10 to the power 3 kilowatts. Right. So I can write that in terms of QH. So I can write that as wet net is equal to m dot multiplied by, okay, let's work with just heat in and heat out. So heat that is coming into the boiler will be equals to H8 minus H5. That's what's across the boiler, H8 and H5. So H8 minus H5, H8 minus H5. That's the heat across the boiler. So that will be H8 minus H5 minus what are we losing? Well, the heat that is being lost is H11 minus H1. So we'll have m dot multiplied by 1 minus y minus z, because that's the fraction, H11 minus H1. You can simplify this to m dot H8 minus H5 minus 1 minus z minus y minus z multiplied by H11 minus H1. Okay, if you like, you can work them out individually. You can start with this is the value for QH. You work it out like this. You can say QH is equals to m dot H8 minus H5. That will be QH. And then QL m dot H11, not a correction, 1 minus y minus z, H11 minus H1. You can just can work those ones out, but then you don't know what this is. If you like, you can work it out per unit mass. Then if you do that, yeah, it works out. It gives you the answer you're looking for. Per unit mass simply means this Q dot over M dot gives you Q, which is equals to Qn minus Q5, and this gives you kilojoules per kilogram, that is per unit mass. You can do the same for the condenser. One minus y minus z, H11 minus H1. Yeah, you can do that if you like. You can work that out separately, but in this case I just chose to do everything at once. Okay, yeah, but cool. So m dot is equal to work net divided by h8 minus h5 minus 1 minus y minus z h11 minus h1. This is 400 times 10 to the power 3 kilowatt divided by what is h8. H8, I know H8 to be 3625.8 minus what is H5? 5 is at 14.59 minus 1 minus what is Y? Y found Y to be, it was Y 0.04926. 0.04926 minus 0. What was Z? Oh, Z. So that is at 0.1762. 0.1762. All of that multiplied by H11 minus H1. H11 was found to be, what was H11? What did we get for H11? Okay, allow me to find H11. 2197. 2197 minus H1. H1 was found to be 198.64. 198.64. Right, dot is equal to, I'll punch that value on the calculator, see what it gives us, divided by 3625.8 minus 814.59 minus 1 minus 0.0492 minus 0.1762. Right, 2197.0 minus 198.64, and that gives me m dot s is 316.61. Question is, what are our units? That's a good question. That's a good question. Are we talking about kilograms per second, or are we talking about kilograms per hour? Let's just confirm that. Okay, kilowatts. We have kilowatts, and down here we have kilojoules per kilogram, and up there we have kilowatts. So kilowatt is the same thing as kilojoules per second. Okay, kilojoules per second. So I can rewrite this as kilojoules per second divided by kilojoules per kilogram. And what does this give me? Well, this tells me that kilojoules over second multiplied by kilograms over kilojoules, that falls away, left with kilograms per second. So my units here are kilograms per second. Yeah. So yeah, that's the mass flow rate. With that amount of mass flowing per second, per unit of time. And now we need to find, what is this? Now we need to find thermal efficiency. Thermal efficiency formula says 1 minus QL over QH. 1 minus what is QL? QL is given by that. I think I can work it out here already. Minus 0.04926 minus 0.1762 multiplied by 2197.0 minus 198.64 give me QL as 1 minus 0.04926 minus 0.1762 2197.0 minus 198.64 gives me 1547.81 kilojoules per kilogram. And QH, well, QH HH minus 814, that is 3625. It's this one here, that expression there, minus 814.59. What does that give us? 3625.8 minus 814.59 gives us 2811.21. Alright, so just made those values. Now all I need to do is just substitute those values in here. Then I'm done. 1547.8 divided by 2811.21. 1 minus gives us 0.4494. 44.9. If you like, you can say 45%. So the thermal efficiency of our plant is 45%. Is that bad? Well, it could be better. But then again, it's better than zero, is it? So yeah, that's how you get thermal efficiency, and that's how you get the mass flow rate. From my side, God bless you and keep you. Continue learning and prepare for the exam. May you shine.